Have you ever wondered, looking at a single image, how far something is? We do this every single day when we play games because we are looking at single images just through our monitor. But we can sort of decipher and sort of demystify how these distances are. We can sort of envision how the world would look in 3 dimensions. How do we actually do that? Let's dive right in and demystify the world of distances from a single image. So as we have seen in the previous videos, simple pixel distances are not enough. What I mean by that is, in a single image, if an object is about 100 pixels long and the same object is about 200 pixels long in a different context, that doesn't mean that the object is like twice as close, right? We need something more than that. To illustrate this point further, let me give you another example. In this case, the red arrow points at the exact same number of pixels, and in the same image, we will see that the same red arrow could mean physically vastly different things. For example, on the leftmost one, it's about a feet of length. In the second one, it's about 3 feet of length, and in the last one, it's about 10 feet of length. The question now becomes, how do we use this knowledge to actually measure distances? So let's look at height from a single image. We have this image, we have the image of this column we were seeing before. And as we project light rays, we will see that the points in the world are spaced irregularly, though they're equidistantly spaced in the real world. This is exactly what projective geometry gives us. And that's what gives us the sense of scale. As we get farther away, distances get compressed, and that's exactly why we see vanishing points. I would urge you to watch the previous video on vanishing points to make this concept really clear. So this is the same reason why you see railway tracks converge to a point in the image, though they're actually parallel and separated by some distance in the real world. Continuing on with the story, we need to measure the height of a human being. Can we just take a picture of the person and then estimate the height? The answer is not really that simple, because you cannot just estimate the height without knowing any other quantities in the image. The question is, what else do we need? Let's do a simple trick. Let's say we are going to place this person on a plane along with a door. We know the height of the door. Now, can we use this trick to sort of use these ratios with respect to the door? What do we actually need for that? Let's look at that. So now let's say the height of the door is capital HR, which is the known reference height of an object. And this doesn't have to be a door, it could be any reference object, as long as we know the height of this reference object and we can estimate the height of the person with respect to that. Okay, so again, in the image, we can easily measure the same object, which is the capital small h in green. Now let's put this point on the ground plane, which is basically the intersection of the door on the floor, right? That's the black point here. And we know that in the image, and we know that in the world point as well. And we are going to reference everything from there as the height. And what we are going to do is we are going to drop a perpendicular from the person's head onto the door to sort of get an idea of the proportion of how much height of the door this person is, right? We'll call that capital H. Okay, great. So, and we also know the top of the door, which is the yellow dot, which is HR from black to the yellow dot. Great. So what we are going to do is, because we know that this is on a flat plane, person and the door are on the same flat plane, which is the ground plane. And what we are going to do is we are going to basically get the 2 vanishing points which are perpendicular to each other and basically join them to get the horizon line. If this concept is unclear, I would urge you to watch the previous video on vanishing points to make this concept very clear. So what we are going to do now is we are going to take the bottom of the foot and we are going to pass it through the vanishing point, and that's going to intersect the door at the base of the door, the black point, which we just saw. So what we want to do now is we want to take and apply the concept of projective geometry, which is basically, if you have a set of collinear points, and in projective geometry what happens is these preserve cross ratios of collinear points, and that's what we're going to use here. So the line, the points have to be on a single line, that means it's collinear, and then we can apply the trick of cross ratios, that it's going to be the same cross ratios both in the image and the same cross ratio in the world plane. Remember, when we do a projective transformation from the world to the image to actually go from 3D to 2D, the projective transformation preserves the cross ratio, which we're going to apply in a second. So again, we are going to take the same vanishing point, we are going to drop again another perpendicular onto the head of the person to actually measure how tall this person is, because that's what we need in the real world. So let's do that, and we are going to basically intersect that on the door, and that's going to be the orange point, which is the ratio of this person's height on the door height. Again, in this particular case, the door is actually larger than the person, so it's somewhere below the topmost point of the door, but it can be actually the other way around as well. Okay, let's continue. So let's call the height of the reference door as HR. Here, the thing on the left hand side with the capital letters is the world, and thing on the right hand side is the image. Okay. Remember, like I said, in perspective transform project, it's like collinear points preserve cross ratios. Basically, the cross ratios in the image plane and the cross ratios in the world are going to be the same, and that's what we are going to utilize. Instead of literal ratios, we have to use cross ratios, and this is what it looks like. Here, capital A, B, C, and D are basically the world points, and little a, B, C, and D are like image from one of the views, and A prime, B prime, C prime, D prime could be an image from a different view. The cross ratios look like this. So we can apply the cross ratios between A, B, C, and D. And again, these points are named arbitrarily, and it could be between the 4 collinear points. And this is how it looks like. The perspective transform is invariant to cross ratio. And again, you can have different sets of cross ratios, which is shown here, and they're related to each other through this quantity lambda. Let's apply this trick to our original problem. So we have the same little h, capital HR, H prime, and so on, where little h is the height of the person in the image. H prime is basically the projection of the person on the door in the image, and HR is the height of the door in the image, and capital H is the height of the person in the world, capital HR is the height of the door in the world. So remember that I said that we have to use 4 points, but we only see 3 points here, the yellow point, the orange point, and the black point. I want you to pause the video and ponder for a second what the 4th point could be. So the 4th point essentially is going to be the vanishing point. In this particular case, in the vertical direction, because the door and the person are both vertical, and they are perpendicular to the horizontal plane, which is the ground plane. So we are going to utilize the vanishing point, which is parallel to both the objects. So in this particular case, it's going to be the vertical point. We're going to take the 2 parallel parts of the door, and they are going to meet. And in this particular case, it happens to be that they meet outside the image. We will call this VZ infinity because it's in the Z direction of the world. Okay, awesome. And this is in the same in the world. Of course, this is going to be at infinity. In the image, it's going to be at some point. So we'll have this H prime infinity in the world, and we'll obviously have the same thing in the image plane as little h prime infinity. And we also have the height from the vanishing point to the yellow point, which is h infinity. So we have all these quantities defined. Let's apply the cross ratio trick. We utilize this particular cross ratio from the previous set, and we will apply the cross ratios as follows. So we know that we are we know that we are applying the cross ratios between the image and the world, because under projective geometry, cross ratios are preserved under perspective projection, and that's what we have done. And then we eventually get this ratio. But remember that, like we had discussed, that simple pixel distances are not enough. We cannot just take ratios of pixels. In this case, we actually have to take the ratios of the cross ratios under projection and the real world. And that's what we will get left with, the quantity on the right hand side on the bottom here. So when we do that, again, like I said, the reference could be anything. In this case, it's a telephone booth from London. So, and you knowing the height of the telephone booth, you can easily measure the height of the person. And in this particular case, it's very, very, very accurate. So the height of the person is about 185 centimeters, and the error is about plus or minus 2.2 centimeters, which is again very, very small, right? And the ground truth height in this particular case was 187 centimeters, which is very, very accurate. This fundamental work is from Andrew Zisserman, who is one of the pioneers in the world of 3D geometry, and I would urge you to have a look at his textbooks if you really want to deep dive into these kind of fundamental concepts. And utilizing this concept of single view metrology, wherein you have a single view and you can basically get the meter scale from a single view given a known reference image and some set of ground plane with a common set of vanishing points. So we can estimate the full 3D geometry of the house or the image itself, because we know that all these are perpendicular to each other just given the height of the person, right? And this is very beautiful. So you might be wondering, these are all great. These are all amazing in the world of math land. But would I really use this, and why would I care about this stuff in the era of deep learning? Would I not just use deep learning to learn depth from a single image? Should I really bother with this stuff? And that indeed is a valid question. Remember that math is always true. So we are going to utilize these mathematical quantities and tricks to make our deep learning networks better, right? In what sense, you may ask? Especially when you're trying to drive in really harsh conditions. If you want to detect lanes, it's really hard because like the lanes might merge with the reflections, the lighting might be really hard, it might actually be very hard to see. So what you can instead do is, like humans, we look at the far distance and we are looking at the vanishing point and we say the lanes are going to meet there. We can utilize similar constructs in the era of deep learning and in the construct of a deep learning framework to actually utilize these methods to do much, much better. And these networks, when trained, actually perform a lot better. And I would urge you to look at this paper for a lot more details. Let's ask the simple question. Okay, this is all great. You're showing us math. Math is beautiful and elegant, but how do we make money out of this?
101st minute. Hurst takes a powerful shot. The ball hits the underside of the crossbar, bounces down onto the line and out. The Germans clear.
So there was a controversy with this World Cup final. What happened was the match between England and West Germany was 2-2 at the 90th minute. And Geoff Hurst's third goal, which basically put England ahead 3-2 in the extra time, that the ball actually hit the underside of the crossbar and bounced. And it was initially unclear if it fully crossed the goal line. But eventually it was awarded by the referee after consulting the lineman, Tawfiq Bahramau. Modern analysis are divided, but let's really find out if it actually was truth. And England claimed victory based on this goal. So what is the controversy about? Let's actually see if this was indeed a goal. The way we would do it is we would say, hey, multiple people are taking pictures of this football match. So we have like two different viewpoints, but we know that the goalpost is a plane. So we can apply a simple homography transformation between the two goal points, right? Everything we have seen in the projective geometry where the cross ratios are preserved, we can totally do the same exact trick in this particular case. So if we do the same trick with respect to the goal line and the markings on the floor, we can actually estimate the three-dimensional trajectory of the ball and project it from the top view. So same idea as the single view metrology with the vanishing points and stuff like that. We just do it with two different views and homographies, and we can actually predict if the ball indeed went into the goal line. If we actually do that, what do we find out? We find out that it was indeed not a goal. And in this particular case, it was 3 standard deviations away from the estimate. So a conservative estimate, the ball is still 6 centimeters away from the goal. And though this was declared a goal, modern technology has shown us that we can go back in time and show that this was not indeed a goal, and that's why the controversy is a very big deal. And again, this is the pivotal work of Andrew Zisselman, and this is one of the foundational things which is used in something called as Hawkeye technologies, which is used to track different kind of like objects like a ball in cricket or in golf to actually get the three-dimensional trajectory of these things so that false goals like the football final does not happen again. So quickly to recap, why can't you just use simple pixels directly for depth? What constraints do you really need to estimate distances from a single view? So hopefully after this video, you know the answer to all these questions, that simply just dividing pixels is not enough. And you need a lot more information in the image to be actually able to do this. In the future episodes, we will see how we can leverage this in the context of deep learning. So stay tuned, subscribe and hit that bell icon and follow us for more. See you later. Bye-bye.